Okay, we started discussing about the second order effects, but somehow we have deviated to understand about the GM and everything. Okay, let us look at now what is the second order effects. Okay, as I told you that the some things that we have seen so far, right? Okay, that is the first thing is when VGS value of a transistor is less than threshold voltage, then we concluded that the IDS value is equal to zero, right? The IDS value is equal to zero. But actually, in fact, where the device dimensions are smaller, that means the length of the channel is smaller and smaller, okay, or short channel devices. This is not true actually, okay. Therefore, there is a non-zero current will be existed. There is some non-zero current will flow. What is that current and how it is? Let us see that one, okay. And another point that we have seen that the threshold voltage of a transistor, right, VTH, is a fixed quantity, is fixed. Okay, under assumption that the source and drain are at the same potential. So we have seen that Vs and Vb body are both are at the same potential. We've seen that one. But if these two are not equal, Vs is not equal to Vb, then definitely there is a change in threshold voltage. We have to see the change in threshold voltage. This is one effect that we can see. And third important one is, so far we have seen that IDS is independent of, is not a function of VDS under the saturation region, right? That means if you keep on increasing the VDS, the IDS doesn't change at all. Okay. Therefore, that is also not true for a short channel devices. Okay. Therefore, but actually IDS is a function of VDS under the saturation. Under saturation. So these are all due to because of course short channel. Short channel. Of course, many short channel effects that are there, but actually we cannot say only these things. But I cannot say that this is actually come under the short channel effect. But VGS is less than VTH. ID is a function of VGS is actually come under the short channel. But in general, VS is not equal to VGS. It cannot come under the short channel effect, but it's a kind of second order effect. Okay. So let us look at the first second order effect. So the first one is called body effect. Body effect. Okay. Okay, if you look at this particular diagram, we have a source, N plus, we have a drain, N plus. On top of it, we have an oxide. On top of it, we have a this thing. Okay. So far we have seen that, of course, there is a body is also there. Okay, let me consider this is a body actually. Okay. This is called P plus body. This is the source. What we have seen so far about the source and body, that means the body must be reverse biased with the source as well as reverse biased with the drain also. Okay. But in this case, you take this is a, for example, drain portion. If you consider this is the positive, okay, this becomes a negative. Okay. This becomes negative. Definitely, since it is a positive, drain is positive, and this is what could be the sign of this one? It can be negative. Okay. If this is the case, then body drain of this NMOS transistor and body of the NMOS transistor both are reverse biased. The drain side, we don't have any problem by keeping the minus. Okay. But what about the source side? Source is also in the negative side. And because of this, it's also negative. If both are at the same potential, definitely it is in the reverse bias. Am I right? The first classes we have seen. If the P and N are at the same potential, okay, and that will be reverse bias. If the difference is there, whether it is a positive difference or negative difference, that's depending upon that one, it is a reverse bias or forward bias. Okay. If both are at the same potential, P region and N region same potential, undoubtedly that is in reverse bias. Okay. So fine. Now, that's the reason why we kept that these both are at the same potential, right? These two are shorted together, and we said that it is a negative potential we apply. If this point is clear. Now, for example, you apply some more positive on the source side. Apply a more positive on the source side. What will happen to if you apply the more positive on the source side? If I'm applying the more potential here, okay. For example, I can say that assume that this is the positive I'm applying. That means body is more positive than that of the source potential. Then what is the PN junction diode here? Is it forward biased or reverse biased? I'm not saying that it is not connected in this way. Okay, the body is at forward bias, and this is at negative reverse bias. If you see the drain side, it is a reverse bias, undoubtedly. If it is a positive or negative, we don't find anything about the drain side. Okay, but is this side you can see what will happen. It becomes a forward bias. Am I right or not? We talk about this particular one. This is the P plus. This is the N plus. We applied here is a positive. Here we applied is a negative. It becomes forward bias. Therefore, we never ever apply the body at the positive potential. Okay, we have to apply because otherwise the current will flow in the body also. Therefore, there is a transistor action will be collapsed. Okay, now what is happening here now? So that means now, as we say, that it's a negative potential that we have to apply. Fine, good. But if it is more negative, we apply it than that of the source potential. If it is more negative than that of the source potential, what you can see? What you can observe? That means P side is actually, sorry, N side is actually, the source side is actually more positive than that of N side, the body side. See, what we can observe here is that this is only small negative. This is more negative. Which one is for highest strength? Source side or body side? Source side is the highest strength. So both they are negative, but less negative we have applied at source. So more negative we have applied at the body side. That means this is a reverse bias actually, but the potential is different. But the potential is different. It's a negative direction, right? Therefore, what will happen here? That means there is a more depletion or less depletion. If this, for example, if only compared to this one, only this 1 minus, this is 2 minus. Okay, that means so some depletion region. That means so this much is a depletion region, for example. Okay, for example, this is the depletion region. Let me write here also. Okay, what is the depletion region for a small value here? This is how the depletion region should be, right? This is actually P plus is actually this is N plus. What is the potential here? More negative. It is a less negative. Okay. So what is happening here now? The distance between this one is small. If you apply more negative, for example, here again, then what will happen? It will be extended this side. Okay, that means the depletion region width will be decreased. Sorry, increased. Increase means what? Depletion region means what? It is an immobile charge. It is a immobile charge. Therefore, that immobile charge will be available here. More immobile charge can be seen under the silicon dioxide. If it is more that you apply, then more immobile charge that will be available. More immobile charges will be available. So what is the cause? What is the problem with this one, right? If the source and body are not at the same potential near the silicon dioxide, you will see more depletion charge. Okay, of course, this is depletion charge is available throughout this region. Okay, throughout this region. But this is more below the silicon dioxide. It is also available the more under the silicon dioxide. Under the silicon dioxide is very, very important for us. Okay, this is this portion. I'm sorry, it becomes very thick, but this portion. Under the silicon dioxide means this is the region. Under the silicon dioxide, if we have a more negative charge, more immobile charge, that's creating a problem. That means what we have to do, we have to apply the more gate potential, okay, to invert the channel, to invert this silicon dioxide region. In the previous classes, what we have seen, if the small depletion region is there or the immobile charge is there under the silicon dioxide, less VGS is sufficient to get the inversion charge. If it is a more immobile charge is there under the silicon dioxide, we have to apply more gate potential to invert the channel. Okay, that means what? It increases the threshold voltage of a transistor. For example, if you 1 volt, if you get a, for example, the threshold voltage of a transistor is, for example, 0.3 volts, for example. Okay, that means if you want to apply a small potential of 0.3, then you will get that one. If the more negative potential is available, more immobile charge is there, that 0.3 threshold voltage will become a 0.4 threshold voltage. Okay, we have to apply now the VGS instead of the 0.3 volts, we have to apply 0.4, we have to apply. Okay, therefore, the threshold voltage of this transistor will affect it if the potential difference between the source and drain is increases. Okay, so you can see here, let me write in this way. So the potential difference between the source and body is positive. Okay, positive. That means what does it mean? The source is more potential than that of a body potential. Though it is a negative direction, but it is, we have to say that when VGS value is positive, then that means that there is a difference between the source and drain. That too, the source is more than that of the body potential. So it leads to threshold voltage change. TH changes will be occurred. This phenomena is called body effect. Okay, what we can call it as body effect. If the body effect is there, what is the consequences? That means the threshold voltage will changes. If the threshold will changes, so definitely we have to apply more gate potential. Okay, that's not acceptable one. Okay, small values of this VGS, the transistor must be on. If the threshold voltage is 1 volt, then we have to apply more than 1 volt that I have to apply the gate. That's not acceptable. Okay, that's not recommended. Okay, small value of the VGS, the transistor must be on. Okay. Okay, what is this equation will tell about this one? The VTH of the transistor is nothing but without the body potential, sorry, without there is no potential difference between the source and body, it is called VTH. But because of this body effect, there is a change here. The change is called gamma times square root of 2 pi f magnitude plus VSP minus of square root of magnitude of 2 pi f. Okay, so how this derivation has come is not a question for us. Okay, it's not necessary for us also. Just we have to keep that where gamma is body effect coefficient, and phi f is Fermi potential. Okay. Initially, what is initial value? This is what the initial value without having any body effect. With the body effect, what will happen? This becomes this extra term will be added together, right? Okay. So that's the reason why if suppose normally we have to connect the body and source at the same potential, which means that what does it mean? No body effect. That means whatever the threshold voltage of the transistor is there, that will be the threshold voltage of the transistor. It doesn't change. But whereas if you look at this one, this is the Vs, for example, this is a VB. If both are not equal, if Vs is not equal to VB, definitely what will happen? VTH will change. So in order to avoid, so is it good that you have to use the body effect or without having the body effect? Which one you should say? The transistor having the body effect is good or without body effect? All right. Without body effect is required. If the body effect is there, what will happen? Threshold voltage changes. We don't expect the threshold voltage to change for the transistor. Okay. Therefore, there should not be any kind of body. If you want to avoid the body effect, what you should do? Maintain the gate and source at the same potential, or otherwise, we have to take the body and apply to the most negative potential. Okay, that's what we can say. But most of the cases, the drain and body are the same potential. We have to make sure that drain and body, sorry, source and the body are at the same potential. Okay, the safe side is, suppose if you want to go and understand about this one, you have to go and apply the body to the most negative potential. Does not give you any kind of. Let us take one example. Let us take one example. We'll do this exercise problem. Right? Find the region of operation of, find example, find the region of operation of transistor where body effect coefficient is 0.45. Actually, body effect coefficient, I think this is also the phi of the body gamma is also have some value. That mathematical equation is there. I will give you that handout and then please check it once. Okay. Gamma is 0.45. Magnitude of 2 pi f is equal to 0.9 and threshold voltage is equal to 0.5. For the two cases, one case is VC at 0.6 volts and this is at 2 volts and this is the source. Okay. Now, this is another transistor. This is 1 volt. This is at 0 volts. This is at 0 volts. This is at 1.6 volts. And this is at 3 volts. Please let me know what is the region of operation of these two transistors. So in this case, what we can see, what is the gate? This is the gate, which is the drain. This is the drain. This is the source. So source is at 0 volts. This is also 0 volts. Therefore, here we have no body effect consideration. Okay. Under this condition, which region of operation this is? What region? VDS is more than that of the gate potential, right? Okay, what is this VDS here? Whether the transistor is on or off. 0.6 is more than that of VGS is more than that of 0.5, therefore 0.1 is extra is there, therefore this transistor is on. Okay, then what about this VDS? Simply it is a saturation. I'm not needless to explain that one again and again. It is in saturation. Okay, so here you can see the body and the source are at the same potential. But as you can see here the source is at 1 volt, the body is at 0 volts. There is a potential difference between source and body, right? What is the potential difference here is 1 volt. Okay, so for 1 volt change, that what is happening here? What is that immediately what you should come into your mind? We have to change the VTH value will be changes. What is the VTH value? Before yeah, this is what 0.5 plus what is this value? Gamma, what is the gamma? 0.45 into square root of, they have given 25F is actually what is the value? 0.9 plus 1 volt minus square root of 0.9. What is this value? This becomes 0.7. This VTH value becomes 0.7 volts. So please check it once. Okay. Okay. What is happening here now? What about the region of operation of this transistor? VTH is changed, right? Then what is happening here? What is the region of operation of this transistor? It's off. As you can see, this is a cutoff because the VGS value is, what is the VGS? What is the VGS here in this case? 0.6. 0.6 is less than 0.7. That's the reason the transistor is cut off. But don't say that without using the body and whether the both are at the same potential. Okay, if you say that this is in the saturation, it means it's meaningless. Okay, or you can say that we tempted to say that the 0.6 is 1. That means the difference is 0.6. The threshold voltage is 0.5 actually. Therefore, it is greater than this one. That's the reason why you should say that it is in saturation. Sorry, it is the transistor is on. Actually, the transistor is not on. Why? Because the threshold voltage of this one is changed. Why the threshold voltage changed? Because there is a potential difference between the source and body. Okay, so that's what we have to remember. Okay, that is what the one effect. Look at another effect quickly. The second one is channel length modulation. Channel length modulation. So this is mainly because of when the device dimensions are shrinking. Okay, that means when the distance between the source and drain is smaller and smaller, this channel length effect will come into the picture. Okay, it is due to mainly, it's due to reduced channel length. Reduced channel length. See, the one point is that the people are running behind reducing the channel length actually. Okay, we started at 1 micron distance to now the people are talking about 4 microns, 2 microns. Okay, so that is we are always trying to reduce the channel length. But whenever you're reducing the channel length, we have to keep in mind that channel length modulation. What is this channel length modulation? We'll look at this one. Okay, look at this. If you take this is a particular structure. Here, this is the source, for example, n plus Let me write this is not the one. This is n plus. This is n plus. Okay. Now this is the distance between the LR, am I right? Okay. We take the same device. Copy. Let me take here. Yes, here. But I want to reduce the length from here to here. And this. Okay. Therefore, now my device is something like this. I reduce the device dimensions in this way. And now the length is here at what is the length here now? This becomes length is here in this way. Right? So this is a long channel. I can say that it's a long channel. This is a short channel. Agreed? Okay. Now what you can see here, what is the observation here? As we keep on increasing the drain potential, what will happen? As we keep on increasing the drain potential, what will happen? Okay, therefore the depletion region of this one will increase. Am I right? If it further increases, that means what is the length of the transistor now becomes? Now it becomes something like this. Okay. Initially, this edge to this edge, right? That is the length initially. Now it becomes L dash, something like this. If it increases further the depletion region, that means you increase the more drain potential. What will happen? Again, the length will decreases, something like this, right? So what is happening here in this case? If we talk about this one, and this is what we are writing, right? This is the ideal characteristics of the MOSFET, right? When we are applying the VDS here, when we are applying the IDS here, we are getting the IDS there. Okay. So because of this, the channel is modified. Channel length is modified from one value to another value. Okay. Therefore, the current is actually not independent of VDS, but it's dependent upon VDS. That means a small amount of the current will flow from there. A small amount of the current will flow. Okay. You see, there is some kind of dependency that you can observe. In the black color curve is actually a straight line. There is no change at all on IDS. But in the red dots, what you can see, there is a possibility of changing the current value. Okay. But this change is very, very small. The change is very, very small under the long channel devices. Because enough length is there actually. It is more, it is a 5% change in the current. 5% change in the current. Okay. But whereas this is not the case in terms of the short channels. Okay. What will happen here? Here also, there is a change here. Apply more potential, there is a change here. Actually, this is a very small, but if you go and so forth, if you do here, what is the channel length? So it becomes something like this. Now it becomes something like this. Now it becomes something like this. Okay. If you go on increasing the VDS value more and more, what we can expect? There is a phenomena called punch through. Punch through means that the source and drain are connected to each other. If the source and drain are connected to each other, there is no transaction action. That actually it is breakdown. The transistor will break down. It permanently damages the thing. Okay, that's the reason why we should not apply. So if you want to increase the if you want to increase the drain current, only option is that we have to increase the VDS value. People will thinking in this way, but we cannot increase the VDS value more and more. Okay, if we do in this one, what will happen? The channel will be very, very less. Definitely, the permanently the transistor will collapse. permanent damage will be. That is called punch through. Okay. So we should not be careful about the punch through actually when we talk about the short channels. Okay. But anyway, but here, as you can see, what about, of course, some reasonable bounds that we talk about, okay, before going to the punch through. If this is what the expected the characteristics, for example. Okay. Now what it becomes? It becomes something like this. Look at this one. There is a huge change that the current is varying with huge change actually, right? So therefore, almost it is 35% of change that we can expect. This is because of channel length. That means here, in both cases, when the drain potential is increases, ideally there is no independent actually, but in reality, in practical, as the VDS is increases, the drain current is also will increases in the saturation. But this value is very negligible in the long channel, but it's very phenomenon significant in the short channel. Okay, so therefore, what is the how the current equation will change under the saturation for the short channel then? Okay, IDS is equal, just we have to use some parameter that is called, we have to make them dependent on VDS, right? Therefore, it is independent of VDS, right? Now we are going to add 1 plus lambda into VDS. Okay, we make them independent in this way, mathematically proven. Just we multiply 1 plus lambda times of VDS, that will show you that the slope of the curve. Okay, so of course the derivation part is also, I'm not going to tell you this one, it's not necessary for this. But one thing that you have to remember is that, okay, if you ask me, then I will do this one, but right now not necessary. But lambda times of VDS is also, we'll say that delta L divided by L. Therefore, where lambda is actually channel length modulation coefficient, and lambda is actually is proportional to L. Okay. If the length is very, very, very small, then lambda factor becomes more and more. Okay. If the lambda value is 0, for example, very less there, for example, then what will happen? That means this lambda is tells us about that what is the changes of the change of this lambda is telling us that change of channel length. Okay, if the channel length is larger, for example, this lambda is actually becomes very small. That means this term will be negligible. If the length is very long, then lambda becomes smaller. That means lambda times of VDS becomes insignificant. Then we have only as usual the same saturation current equation. If the lambda is if the length is very, very small, then what will happen? Lambda becomes more. That means this particular term becomes significant. Therefore, there is a possibility of linear current equation. Some variations of the current can be seen there. Okay. So that's the reason why when you do the simulations in your laptop by using the spice model and everything, we are expecting that the under the saturation is a straight line actually, but it won't happen. Even if it's a long channel or small short channel, is a small increment that you can see. But that increment will be very, very less in long channel, but very large in short channel. Okay. So if you want to calculate the value of this one, you have to use this one. Is it point is clear to everyone? What is the channel length modulation? Okay. The current equation, what is the channel length modulation? Channel length modulation tells us that the ID value of the MOSFET under the saturation is not independent of VDS, but it's actually depending on VDS value. Okay. So is it a good phenomenon, bad phenomenon? What you're expecting? There should not be any kind of channel length modulation in your MOSFET. Okay. It must be low. Why? Because under the saturation current, you are operating the MOSFET in saturation for the analog applications. Under the saturation only, you will get the amplification phenomena. Okay, more amplification is observed. Why we are not using the MOSFET in the linear region? For the amplification purpose, because the gain is very small. Okay, but in the saturation region, gain is very high. That's the reason why we want to operate. The gain is high means that under saturation means that independent of VDS. If you make that dependent, definitely it is some kind of slope is there. Because of the slope, definitely you won't get any kind of. Because of that one, you don't get any kind of the gain actually. Okay, let me explain a little bit here. Let me go here in this way. For example, this is this equation. Okay, this is what actually you can see. Okay, see the difference between these two is more than that of difference between these two. If the channel length, if you take the channel length device MOSFET under the saturation region, okay. So the change in the VGS here, look at the change in the VGS here. Actually, what is happening here? Change in the IDS is more, right? Change in the IDS is more. Whereas in the short channel channel length modulation is considered, the change in the VDS does not give you that much great impact of this one. This is very, very small thing is there. Here is very small. For example, region 1, this is a region 2. Therefore, 1 is greater than 2. Okay, that means the ID, for example, ID1, this is the ID of I1, this is ID of 2, is very, very small. That's the reason why the transistor should not have any kind of channel length modulation. We have to reduce that one by using some other means, but the ideal characteristics of the MOSFET should not have channel length modulation. Okay, so the last one, subthreshold conduction. Subthreshold conduction. Subthreshold conduction. What is the subthreshold conduction? As we have seen that when VGS value is less than threshold voltage, the MOSFET is off. Therefore, IDS is equal to 0. But because of the subthreshold conduction, okay, then even when VGS is less than VTH, the IDS value is not equal to 0 since subthreshold conduction. So why this phenomenon is observed? Because of the short channel again. It is also because of reducing the length of the transistor. This kind of phenomena will come into the picture. It is actually a leakage, because this is called a leakage current. We can also call it this. Okay, but actually we cannot say directly leakage current. But actually leakage current is from more or less we can call it as this one. Let us look at this one. Better if this can be evaluated more effectively on the logarithmic scale. For example, log ID, if you take, for example, look at this. This is called ID versus a VGS. Am I right? Okay, what is this ID versus a VDS? Something like this, it will go and go in this way. Am I right? Therefore, before threshold voltage, we are not able to get any kind of current here. Did you catch this point? VGS value is less than threshold voltage, there is no current. But this can be, but there is an amount of the current will flow, but some amount of the current will flow, something like this, but it's very difficult to capture this particular information in the linear scale. Okay, we take in the logarithmic scale. So we take the logarithmic scale. This is called VGS, but this is a log ID. Okay, so this is going in this direction. It's going in this direction, but look at this one. This value will go and come to this point. It is little bit 10 to the power of minus 12. Okay, this is called the threshold voltage. So as you can, we are expecting that less than threshold voltage, there is no current. But because of this one subthreshold conduction, some amount of the current will flow here, right? Okay. Actually, this should be 0. But here some finite value is that finite value is 10 to the power of minus 12 in the order of picoseconds or sorry, picoamperes or femtoamperes. It may be in the order of picoamperes or femtoamperes. Okay. This point is clear. So what is this mathematical equation that governs this phenomena? Okay. Therefore, here ID is nothing but I naught into e to the power of VGS divided by neta VT. Okay, this is what we have to think about it. Okay, where VT is not threshold voltage, it is nothing but KT divided by Q, therefore thermal voltage. Okay, this explanation, this derivation is also not required for you. Just you understand about there is a subthreshold conduction here. Okay, I will give you one scenario. You please let me know which one you feel better. Okay. Okay, of course, actually, when VGS is less than the threshold VTH, we are not going to operate in the saturation region. It is in the linear region. Therefore, for the analog designers, this is may not be the problematic thing, but digital designers is very, very important for them. Why? Because they want to operate in the transistor in the linear region. Okay, so that's what you have to remember. But means in the linear region, you want to use this one as a switch. Okay, so you look at this one. In the linear region, MOSFET can act as a switch. Okay, on or on switch. Okay, in the saturation region, MOSFET can act as a current source, constant current source. Okay, we'll talk about more a little bit later. For example, look at this one. Two things I have given here. This is called M1. This is called M2. The transistor one behavior is something like this. This is a log scale, log ID, and this is called the VCS, for example. Okay, this is actually changing 80 millivolts per decade. That means that when VGS value is change, the VGS value changes, for example, 80 millivolts, then it is decay, then that will be dropped by 10 times, 10 decades, for example. So for one decade change, how much VGS we have to apply? 80 millivolts that I have to apply in this case. So one decay change of the current, one decay change of the current going downwards, how much VGS we have to apply? 80 millivolts. Okay. For example, in this case, 50 millivolts per decade. What does it mean? If you want to drop ID by one decade, how much VGS I have to apply? 50 millivolts. A small change of 50 millivolts will go to one decade drop, whereas 80 millivolt change is required to go down to one decade. Which transistor is suitable for a better switch? Switch one is M1 transistor M1 is better or M2 is better? It should be M2 is better. Why is M2 is better? A small change of this one will go drop by one decade change. A small 50 millivolts. Because what is our expectation? The current must go down to 0 immediately. It is less than threshold voltage, right? Less than threshold, we don't expect any current. But even the current is there. If you go very fastly, then it's the best choice, right? That's the reason why. So 50, a small change of VGS will go drop significantly, then that is a better switch. But here, how much we have to apply here? We have to apply 10 millivolts VGS change is required to go down to 1 decade of change of IDs. Okay, so that's what we have to remember. So which one? Of course, for you analog designers, don't worry about this one. is simply because of we operate in the saturation region, we don't operate at all in the linear region at all. Okay, we can consider this. Is this point is clear to everyone? What are the second order effects? Only the channel length modulation, body effect, and subthreshold conduction. Okay. In all the three cases, I have given the mathematical equation for the current. What is the ID here? What is the ID here at this case? What is the consequences of threshold voltage of this? Okay. So very, very important in the examination point of view also. In the interview point of view also, people definitely ask, okay, tell me something about the channel length modulation, or tell me something about the subthreshold conduction, or something about the body effect. Okay, we stop here today, and we'll see in the MOSFET models in the small signal models in the next class. Thank you.